Welcome to Beyond the Brackets. In this video, we continue our discussion on particular integrals of type 4. Type 4 involves a combination where type 1 function is multiplied either by type 2 or by type 3 function. In other words, we deal with expressions like an exponential function multiplied by trigonometric function or exponential function multiplied by a polynomial. To solve the particular integral, we begin with the exponential term e power ax, where the operator d will be replaced by d plus a. Let's look at the first question. First, we write the operator form of the given differential equation by replacing d by dx with d. So we get d square minus 7d plus 6 into y is equal to e power 2x into 1 plus x. Its auxiliary equation is given by replacing d with m and equating it to 0. We get m square minus 7m plus 6 is equal to 0. The roots of this equation are m is equal to 1, 6, which are real and distinct roots. For this, the complementary function is given by yc is equal to c1 e power x plus c2 e power 6x. To find the particular integral, take the reciprocal of operator form and apply it to the right hand side. So we get 1 by d square minus 7d plus 6 multiplied with e power 2x into 1 plus x. Here the right hand side is of the form e power 2x, which is type 1, multiplied by 1 plus x, which is type 3. Therefore, this belongs to type 4, where an exponential function is multiplied by a polynomial. To proceed further, we solve the exponential term first by replacing d with d plus a, where a is the coefficient of x and here it is 2. So we get d plus 2 whole square minus 7 into d plus 2 plus 6. Now simplify the operator d plus 2 whole square, which will be d square plus 4 plus 4d. Next we get minus 7d minus 14 plus 6. All the terms further simplifies to d square minus 3d minus 4. Next we solve for 1 plus x, which is type 3. We take the constant term common from the denominator. So we take minus 4 common to get 1 minus of d square minus 3d by 4. Next take the denominator to the numerator and expand using the formula 1 minus d inverse, which will be 1 plus d square plus d cube and so on. Here d is d square minus 3d by 4. Now the RHS is 1 plus x. When we differentiate this, we get differentiation of 1 plus x will be 1. Second order derivative and higher order derivatives will be 0. Therefore, we only need to consider terms up to the first derivative d, since higher powers like d square, d cube and so on will be zeros. So the expansion will be reduced to 1 minus 3d by 4. 1 into 1 plus x will be 1 plus x and minus 3 by 4 into differentiation of 1 plus x is 1. Simplifying this further, we get x plus 1 by 4. The solution is given by y is equal to yc plus yp. Substitute the values, both the terms, and that will be the solution of the first question. Let's look into the next question. The operator form is obtained by replacing d by dx with d to get d square plus 1 into y is equal to e power minus x plus x cube plus e power x into sin x. For the auxiliary equation, replace d with m and equate the equation to 0. We get m square plus 1 is equal to 0. The roots of this equation are m is equal to plus or minus I, which are complex roots. For the complex roots, alpha plus or minus I beta, complementary function is given by e power alpha x into c1 cos beta x plus c2 sin beta x. Here alpha is 0 and beta is 1. So yc will be equal to c1 cos x plus c2 sin x. To find the particular integral, take the reciprocal of the operator form multiplied by the RHS. Here RHS has e power minus x, that is type 1, x cube, that is type 3, and e power x into sin x, that is combination of type 1 into type 2, so that will be type 4. So all these terms will be solved separately. To solve the first term, that is e power minus x, which is type 1, we replace d with a. Here a is the coefficient of x, that is minus 1. So this becomes minus 1 whole square plus 1 into e power minus x, it is e power minus x by 2. That is the solution of the first term. Next, solving the second term, x cube, which is type 3. We try to make the constant as 1 by taking it common, but here the constant is already 1. So this is already in the form 1 plus d square. Taking this to the numerator, this becomes 1 plus d inverse. The formula is 1 minus d plus d square minus d cube plus so on. Here d is d square. Expanding this, we get 1 minus d square plus d power 4 minus d square whole cube plus so on. We have x cube on the right hand side. Differentiating x cube, we get 3x square. Applying d square, we get 6x. Applying d cube, we get 6. Higher order derivatives becomes 0. So for x cube, we only get non-zero terms up to d cube and all higher powers will be 0. So while expanding the formula, we keep the terms only up to d cube. Now the formula is reduced to 1 minus d square into x cube. 1 into x cube will become x cube minus d square will become 6x. That is the solution of the second term. Now let's move on to the third term. Here we have an exponential function multiplied by sin x, which is type 1 combined with type 2, making it type 4. To solve this, we first handle the exponential term by replacing d with d plus a. Here a is the coefficient of x, which is 1. So we get d plus 1 whole square plus 1. Expanding d plus 1 whole square, we get d square plus 2d plus 1 and plus 1 will become plus 2. Now to solve for sin x, which is type 2, we replace d square with minus a square. Here a is equal to 1, so we get minus 1 plus 2d plus 2, which simplifies to 2d plus 1. To solve this further, we rationalize by multiplying and dividing by 2d minus 1. So the numerator becomes 2d minus 1 into sin x and the denominator becomes 4d square minus 1. First solving the denominator by replacing d square with minus a square, that is minus 1, we get minus 4 minus 1, that is minus 5. Now solving the numerator, 2 into differentiation of sin x is cos x minus 1 into sin x. Solution is given by y is equal to yc plus yp. Substitute the values of both the terms and that is the solution of the second question. The last question is already given in the operator form. To write the auxiliary equation, replace t with m and equate it to 0. We get m square plus 1 is equal to 0. The roots of this equation are m is equal to plus or minus I, which are complex roots. Complementary function for this will be yc is equal to c1 cos x plus c2 sin x. Yp will be the reciprocal of the operator form, that is 1 by d square plus 1 multiplied by the RHS x square into cos hx. Cos hx belongs to type 1, where it can be written as e power x plus e power minus x by 2. Both the terms will be solved separately. For the first term, the right hand side contains e power x, that is type 1, multiplied by x square, that is type 3, making it type 4. To solve this, we first handle the exponential term by replacing d with d plus a, where a is the coefficient of x, which is 1. So we get d plus 1 whole square plus 1. Simplifying this further, we get d square plus 2d plus 2. Now the RHS has x square, which is type 3. Here we take the constant common, that is 2, to get 1 plus d square plus 2d by 2. Taking this term to the numerator, it becomes the expansion of 1 plus d inverse, which is 1 minus d plus d square minus d cube, so on, where d is d square plus 2d by 2. We have x square on the RHS, for which differentiation will be 2x and d square will be 2 and higher order derivatives will be 0. So we include the terms only up to d square. Simplifying this, we get 1 plus d square by 2 minus d into x square. Now 1 into x square will be x square plus d square of x square will be 2 divided by 2 minus d of x square will be 2x. So this term is simplified to x square minus 2x plus 1. Solving the second term in the same manner, it is also a type 4, which is a combination of type 1 and type 3. Again, we'll first solve e power minus x, where d will be replaced by d plus a. Here a is minus 1. We get d minus 1 whole square plus 1. Solving this, we get d square minus 2d plus 2. Again, x square is type 3. For this, we take the constant common. So if we take 2 common, we get 1 plus d square minus 2d by 2. Taking this term to the numerator, it becomes the expansion of 1 plus d inverse, which is 1 minus d plus d square minus d cube plus so on. Here d is d square minus 2d by 2. Again, RHS is x square, for which differentiation will be 2x and d square will be 2 and higher order derivatives will be 0. So we'll include the terms only up to d square. Simplifying this further, we get 1 plus d square by 2 plus d into x square. So 1 into x square will become x square plus d square of x square will be 2 divided by 2 plus differentiation of x square will be 2x. So this term simplifies to x square plus 2x plus 1. Solution is given by y is equal to yc plus yp. Substitute the values of both the terms and that will be the solution of this question. 2 more questions of type 4 along with their answers are included here.